Okay, let's dive right into this incredible molecular story. We're going to go inside a single bacterial cell to get to know a machine that is honestly more intricate and essential than pretty much anything humans have ever built.
So this is the big question, right? It's the fundamental challenge we're looking at. A problem of pure efficiency and survival that bacteria, it turns out, have solved in a really elegant way. I mean, this is a high-stakes decision that's happening trillions of times a second, all over the world, all around us.
So to really appreciate the genius of the solution, we first need to get our heads around the sheer scale of the problem these tiny little organisms are up against.
Okay, think about a bacterium like E. coli. Its DNA library has something like 4,300 different genes. But, and this is the key, it only has about 4,000 little machines available to read them. These are called RNA polymerase. So right away, you've got this intense competition. It's like a constant traffic jam where only the most important genes can get read at any one time.
All right, so let's properly meet the hero of our story, this all-important machine that reads the DNA blueprint and really kicks off the entire process of expressing a gene.
So, at its core, transcription is just that first critical step in bringing a gene's instructions to life. You can think of it like photocopying a single recipe from a massive, priceless cookbook. That way, the kitchen gets the instructions it needs, but the original book stays safe and sound.
Now, this machine isn't just one solid piece. It's a whole complex. You've got the core enzyme, which is kind of the engine that does the heavy lifting of building the RNA. But the real genius here is this other part, the sigma factor. Seriously, think of it as a super-specific GPS unit. It snaps onto the engine and guides the whole thing to the exact start here sign on the DNA, the promoter, for the one gene that the cell needs right now.
But here's where things get, well, a little weird. This powerful, precise machine doesn't just lock on and go. It stutters. And for decades, this strange little inefficiency right at the beginning of the process had scientists completely stumped. So when you look at the official steps for getting transcription started, you see this bizarre third step called abortive cycles. I mean, the machine binds, that makes sense. It unwinds the DNA, okay. But then it just sort of spins its wheels. It makes these tiny, useless-seeming little bits of RNA before it can finally break free from the starting line.
This all leads to one fundamental question. Why on earth does this abortive process even happen? It just seems so wasteful. For years, scientists had a few different theories about what was really going on under the hood.
You know, the early ideas were pretty intuitive. People thought maybe the entire machine just kind of rocks back and forth on the DNA, or maybe it stretches out like an inchworm, with its front end moving forward while its back end stays put. But, you know, neither of those models really fit all the data that was coming in.
The reality turned out to be so much more elegant, and honestly, it's kind of mind-blowing. The machine stays completely still. Instead of moving along the DNA, it actually grabs the DNA ahead of it and pulls or scrunches it into its core. It just keeps pulling more and more DNA in, building up this incredible stress, almost like winding a rubber band tighter and tighter. So this scrunching action builds up a huge amount of tension. Those little abortive RNA bits get released while the tension is building, but eventually that coiled spring gets so tight that it just snaps. And the release of all that stored energy is what physically launches the polymerase off the promoter and sends it rocketing down the DNA to do its job.
Okay, so the machine's off and running. But its speed isn't just constant. Nope, it's tightly controlled by a whole different set of proteins that act like traffic cops, creating this really complex regulatory system. Two of these proteins, NusA and NusG, are the real stars here. You can think of them as a brake and a gas pedal. NusA hops on and encourages the polymerase to pause, slow things down a bit. NusG does the exact opposite. It jumps on and helps the polymerase power through any tricky spots, cranking up the speed and making sure it doesn't fall off the DNA.
And here's why this is so important. This regulation makes sure that transcription doesn't get way ahead of translation, which is the next step in making a protein. In bacteria, these two processes are actually physically linked together. NusG literally forms a bridge between the polymerase and the ribosome, creating this perfectly synchronized, hyper-efficient assembly line that goes directly from gene to protein. It's just brilliant.
So now that we understand this machine so well, how it starts, how it runs, how its speed is controlled, a whole new question comes up. Can we break it? On purpose? And that is exactly what the powerful antibiotic rifampicin does. It doesn't mess with the engine's active site.
Instead, it binds nearby and acts like a physical wedge, jamming up the exit channel. So the polymerase can start making a new RNA chain, but after just 2 or 3 links, that chain hits a dead end. The whole process just grinds to a halt.
But of course, bacteria are incredibly resilient. For them, this is life or death, so they've evolved some really clever ways to fight back. The most common way is just a tiny mutation in the polymerase itself that stops the drug from even being able to grab on. But they can also make enzymes to destroy the antibiotic, or even install little pumps in their cell walls to physically spit the drug back out.
And this is what really shows why understanding this microscopic machine matters so much. This isn't just some abstract science experiment. Rifampicin is a cornerstone of modern medicine. It's a critical frontline drug in the fight against really devastating diseases like tuberculosis. This molecular battle we've been talking about, it's happening inside patients, right now, all over the world.
So this constant evolutionary arms race between our best medicines and the bacteria's defenses leaves us with a final, really crucial thought. Understanding every single gear and lever of this machine, from its weird stutter star to its speed controls, well, that's the key to staying one step ahead and designing the next generation of smart drugs that can keep us all safe.